Hello, everyone. Welcome to our webinar today. I'm Thomas von Larcher. I'm managing editor of the journal SN Applied Sciences, and I had to run the meeting today. Today we have Professor Matteo Giancomini from Universitat Politècnica de Catalunya with us, and the university is recently referred to as Barcelona Tech for short. I would like to introduce Professor Giancomini. Dr. Giancomini is Assistant Professor in Computational Engineering at Barcelona Tech and affiliated faculty at the Institute of Mathematics at Barcelona Tech as well. He received a PhD in Applied Mathematics from École Polytechnique Université Paris-Saclay, France in 2016. His research activities lie in the field of computational science and engineering, with particular emphasis towards the simulation of flow phenomena for industrial purposes. And I should not forget to mention that Dr. Giancomini is guest editor of the journal's topical collection, Adaptive Model, Mesh and Resolution Techniques for Computationally Demanding Problems in Simulation-Based Engineering. So coming back to our webinar today, we will have time for questions after the talk. So please type your question into the chat box as we go, or after the talk, you can unmute yourself and ask your question. With this, I would like to welcome Professor Giancomini again. Matteo, it's my pleasure to have you on our webinar series today. And the floor is yours.
Thank you, Thomas. My pleasure being here. First of all, let me thank Thomas and the organizers for the kind invitation. Let me see, let me share my screen. Okay, so today I'm going to talk about devising surrogate models to solve parametric flow problems. As Thomas mentioned, this is related to application in CFD, specifically towards an industrial viewpoint. And before diving into the details, let me just give a brief picture of why, of how this research relates to the topical collection that I've been co-editing with Enrique Nadal from Universitat Politècnica de Valencia. So the research, the topic of the topical collection is adaptive model, mesh and resolution techniques for computationally demanding problems in simulation-based engineering. So what we were thinking about with Enrique was the solution of complex multiphysics problems, which are ubiquitous in physical sciences and engineering, using simulation-based techniques, so computational engineering. And specifically, we are interested in problems that involves multiple queries in order to perform real-time decision-making, design, control, and optimization inverse analysis. And in order to solve this problem, we rely on reduced order models, error estimation, adaptivity techniques, and application of HPC. So this is the global picture that I will try to address with some recent results that I'm going to present. But first of all, let me acknowledge my collaborators: Antonio Huerta from UPC SIMNA in Barcelona, Ruben Sevilla from Swansea University, and Karsten Ottmer from Volkswagen Corporate Research in Wolfsburg. All the results that I'm going to present are related to my former PhD students, Vasilis Tsiolakis, who is now postdoc at NTNU, Jordi Villa-Perez, who's now postdoc at MIT, and Luca Borchini, who's now mathematical analyst at BMM Test Labs. And of course, last but not least, the support of the funding agency, the European Commission, the Spanish Ministry for Economy and Competitiveness, and the government of Catalonia. So let me start with the motivation of this work. This work actually goes back to a collaboration that we've been developing for some years with Volkswagen Corporate Research. And these results that I'm showing are part of the PhD thesis of Vasilis Tsilakis. So in the context of the problems that our industrial partners solve at a daily basis, the main bottleneck is represented by the necessity of performing parametric studies. Parametric studies means solving problems with slight variation of a set of parameters, which may be the domain, the boundary condition, or the condition in which the system is working. Solving such problems multiple times in order to understand which is the best or the optimal in some sort of configuration that we would like to solve. And this is the case, for example, of this heat ventilation air conditioning duct that I'm showing here. We are applying a jet on this red patch. And what we observe is basically a variation of the recirculation bubble in this region. And so we can actually perform some flow control analysis in order to optimize the performances of this problem. I will go back to it later in the presentation. So what I want to highlight, first of all, it's the difficulty associated with this problem, which is the necessity of solving multiple queries of the same problem using different parametric settings in order to be able to perform interactive control and optimization. So there are mainly two questions that I will try to address. The first one is, how can we efficiently test a large number of configurations? And the other one is, how can we evaluate different scenarios in real time? These are basically the two ingredients that I want to, the two problems that I want to address. And in order to address them, we will rely on surrogate models. So surrogate models have been called in several different ways in the literature: reduced order models, some meta models. So basically the idea is some sort of black box in a way that allows us to have an information of the output of the system given a specific value of the input, and the input are our parameters. Specifically, I will focus on proper generalized decomposition. And remember that the challenge that you're facing is efficiently computing multiple queries of a given problem in order to be able to perform real-time simulation. So the idea is to split the resolution of our problem in two phases. One phase, which is called offline simulation, in which we perform some computation on a fixed reference geometry and on a fixed mesh in order to construct what we call a parametric solution, a generalized solution, which in our case will be the proper generalized decomposition-based surrogate models. You can think about these surrogate models as a black box, a magic box. It will be our PGD box in this case. So this simulation, of course, can be computationally expensive. Generally, it's performed on supercomputers, but it's performed only once. This is the key aspect. Then, in order to understand how the solution changes depending on the value of the parameters, we perform what we call an online evaluation. So we take a parameter mu. This parameter mu may describe the geometry or the physical properties, the boundary condition of our system. We take this parameter mu, we plug it into our PGD box, and in real time, our PGD box will give us as output the solution, which of course is a function of space, evaluated for the specific value of the parameter mu. The key aspect is that this online evaluation is computationally inexpensive, but this is the goal, and generally can be performed on any laptop device or portable device. It can be performed even on a tablet, okay? So the computational burden is those hidden in this first step, and the second step is what allows us to perform real-time studies. So how do we construct this PGD magic box? Well, we rely on the work by Marmok, Chinesta, and Koenigs. And the idea is that we want to construct a rank-n separable approximation of our solution. So we have our solution U, which is approximated by U PGDN. And this U PGDN is the sum of n terms. And these terms are separated in the sense that are either function of the space or function of the parameters. So henceforth, I will represent in red everything which depends on space, and in green everything which depends upon parameters, in order to visually understand better how the methodology works. So how do we compute this solution? We rely on an alternating direction scheme. So it's a greedy approach. We assume that the term n-1 is known in order to compute the term n. And specifically, we project onto the tangential manifold, alternately along the spatial or parametric direction. So I don't want to enter into too many details, but basically the idea is that we end up having this iterative method in which we have what we call a spatial iteration, in which we fix the parametric modes, which are the phi's, in order to compute the spatial modes, our FUs in red over here. Then with the latest computed spatial modes, we fix them, and we compute the parametric modes during our parametric iteration. And we iterate until a given convergence criterion is fulfilled. So the first contribution that I want to show you is the construction of surrogate models that are non-intrusive with respect to Openform. Openform, as many of you know, is one of the standards in terms of CFD solvers available. It's open source, but also available generally in the industry. So the idea is we want to construct a PGD algorithm, which is our algorithm over here, remember, in which the spatial problem, the spatial iteration, which in this case will be the steady incompressible Navier-Stokes equation, is solved using Openform as a black box. Specifically, each time that we need to solve a spatial problem, we call the simple form algorithm in Openform without any modification. So what is the difference with respect to classical solution, where we a priori compute some coefficient that will need to multiply all these terms, but the solution itself is simply performed using Openform with the simple algorithm. Once we have this solution computed, we then go to the parametric iteration. And in parametric iteration, we end up having a system of algebraic equation, which in this case is solved, for example, using a collocation approach. So let me show you some results of this first methodology. This is part of the PhD thesis of Vasilis. And here we have a non-leak cavity with parameterized jets. So we have here a velocity of the lead, which is 10 meters per second. On the four corners, we are adding jets with peak velocity that span from 0.2 to 2 meters per second. So we are Reynolds number 1000, okay? So what I report here on the top is the evaluation of our surrogate model, our PGD solution for different values of the parameter under analysis. The parameter, remember, controls the amplitude of the jet. And at the bottom, the reference solution computed using Openform. So qualitatively speaking, you can observe that more or less you could say, okay, the solution is rather okay. If we actually zoom in, remember the top is the surrogate model and the bottom is the reference solution. We observe that the PGD surrogate model is actually able to capture precisely localized feature of the flows and topological changes, so appearance and disappearance of the vortices. And what's important in this context is that in order to compute the generalized solution at the top for all the values of the parameter, we need between 4 and 6 full-order solver, whereas where each full-order solver is basically the cost of computing one of the figures below. So at a limited over cost, we are able to have the solution available for all the range of parameters under analysis, and then perform online our studies in order to perform optimization for control and so on and so forth. So of course, the following step was verifying in a problem with a real dimension. And here I'm back with the HVAC duct that I've shown at the beginning, Reynolds 280, and the restriction again are using finite volumes, specifically Openform, and being non-intrusive with respect to this solver. What we are doing is in this region over here, we are adding a jet, and this jet spans from blowing to suction. The first thing, of course, the effects are extremely different in this two range of the parameters. The goal is reducing the recirculation bubble that develops over here. And what we observe is that experimentally, that the error in velocity and pressure is below 2% from the surrogate model with respect to the reference solution computed using Openform. But in this specific problem, actually, what we are really interested in observing is neither the velocity nor the pressure field, rather a specific quantity of interest, which is the pressure drop. And again, the pressure drop the error in the pressure drop is below 2%. What is more, we can construct separated response surfaces. So how the quantity of interest, which is our pressure drops, varies as a function of the parameters. And here I'm reporting as a dashed black line the solution of the surrogate model and how it compares with the solid line, which is the reference solution. So again, we have good agreement well within the range of acceptability of industrial precision. So the natural evolution was extended this framework to turbulent Navier-Stokes. This was the second part of Silva's thesis. And in this case, we relied on Erran's framework, so Reynolds average Navier-Stokes equation with the Spalart-Almaraz model, which is the traditional turbulence model that is employed in Volkswagen to perform turbulence simulations. So here we have a NASA wall-mounted hump at Reynolds almost 1 million. And what we are doing in the rear part of the hump, I'm just presenting the last part of the domain. On this rear part of the hump, we are applying a suction jet with a peak velocity that spans from 2 to 23 meters per second. Again, we have the surrogate model at the top, the reference solution at the bottom. The first thing that we can observe, as expected, is that increasing the value of the suction jet, the recirculation bubble decreases. And here we can see the vertical line, which represents the position of the reattachment point, which of course gets closer and closer to the body when we introduce more suction. And most importantly, it's in excellent agreement with the reference solution from Openform. Indeed, if we look a bit more closely to the position of the reattachment point, we see that within the range of the parameters studied, the error is always below 0.5, 10 minus 2. So the methodology is indeed able to construct surrogate models, being non-intrusive with respect to Openform, and this methodology is applicable both to laminar and viscous laminar and turbulent flows. Now, everything works good in the context of Openform, but there's still a limitation, which is indeed intrinsic to the solver, which is the requirements that Openform, as well as many other finite volume solvers, have in the context of the quality of the mesh. So those finite volume solver, both cell center and vertex center, tends to suffer when distorted meshes are employed or extremely skewed and stretched meshes are employed. This, of course, is a limitation in the context of industrial flow problems, because generally speaking, we work with complex geometric configurations. Here I'm reporting a microchannel, a drone, or a mechanical piece. And the other restriction stems from the fact that automatic mesh generators exist, both open source and commercial, but they tend to work more on relying on tetrahedral cells. Whereas Openform solvers, for example, outperforms other solvers when hexahedral cells are existing. Of course, there are mesh generators that employ hexahedral elements, but automatic mesh generators for hexahedral meshes or hexahedral elements is still an open field of investigation. So the drawback that we identified was the necessity to develop a new robust finite volume solver, which is capable to handle unstructured meshes and moreover is insensitive to mesh quality. So we would like to be able to run our simulation on meshes like these ones. And for this reason, we introduced, I'm going to briefly talk about the Loworder CFD solver insensitive to mesh quality, which is the face-centered finite volume paradigm. I don't want to enter into too many details, but the basic idea is that the face-centered finite volume method relies on introducing a constant approximation of the variable on each face, which is represented in here by this dot along the faces. Of course, there are some nice properties that I want to briefly discuss with you. The first one is that the methodology does not require any flux reconstruction. It does not require any shock factoring in presence of discontinuities, and it does not require pressure correction in the incompressible way. So let me dive a bit into some details. The first one is the robustness to the mesh quality. And this is the case of a Stokes problem with an analytical solution that we've tested using regular grids, distorted grids, or stretch grids with stretching factor up to 1000. The results that I'm showing are for triangles, but actually we extended also to quadrilaterals, hexahedra, tetrahedra, prisms, pyramids, and everything's work in a comparable way. So here I'm reporting the convergence of the L2 error with respect to the mesh size for the velocity, the gradient of velocity, and the pressure. And what we observe is that we get first order convergence for all these variables, and most importantly, independently of the quality of the mesh. So we have no loss of accuracy, even in presence of distorted grids or stretched grids, okay? This is important, and here specifically, we get convergence of order 1 for the gradient of the velocity without any need of reconstruction of the fluxes. This is the major difference with respect to existing finite volume solver. Of course, we are paying the fact that we have much more phases in a mesh than cells. So globally, the number of degrees of freedom involved in the simulation is larger, but they may employ more general meshes with much less restriction. Okay, having this in mind, in the context of the PhD thesis of Jordi Villa-Pérez, we tested the methodologies for compressible flows. Specifically, this is transonic implicit flow over a Numenera M6 wing. This is Mach number 0.8, and we are solving with the first center finite volume with HLL numerical flux. And here I'm reporting the distribution of the pressure on the wing. This is the well-known lambda shape shock that develops. And here I'm reporting the pressure coefficient at this section of the wing. I'm comparing with the dots which represent the experimental solution. Green and blue are second order finite volume solver, respectively cell center from Fluent and vertex center from Flight. And in red, we have the phase center finite volume method. So we observe that we have accuracy comparable with second order solver. Of course, they are more precise in this region because they are second order indeed. But most importantly, we get a non-oscillatory approximation of this shock, whereas the cell center and the vertex center present this undershoot here in presence of the shock. And finally, all this is performed using an unstructured mesh of 5 million tetrahedral cells. So we have indeed a solver which is robust and insensitive to mesh quality in compressible flows. Of course, we are interested also in incompressible flows. So we pushed the simulation to viscous incompressible laminar flow past the cylinder. This is Reynolds 30 for different values of the Mach number, 0.1 and 0.01. So what we observe is that the method is robust in the incompressible limit, and we don't need any pressure correction for this methodology. We've done it for viscous incompressible. We can push it even more. This is a collaboration with Ruben Sevilla going to microfluidics, so neglecting every contribution of inertia. So here we have an application of the Stokes equation to microfluidics. This is a microchannels with 39 red blood cells. I'm showing here the streamlines with the pressure distribution on the red blood cells and three snapshots of the velocity, three sections, sorry, of the velocity. What's important here to observe is that we have a problem with a complex geometry, almost 9 million tetrahedra, 61 million of unknowns, and computation and assembly of this problem takes slightly more than 1 hour. It's important to observe that this code was implemented in MATLAB. It's a serial code, so there's much room for improvement for the solution of this problem. And this was published a couple of years ago here on the journal. So the following step in the context of microfluidics was testing other challenging geometries like this microswimmer over here. And again, with Ruben Sevilla, we extended the framework to have second order convergence, second order accuracy of the primal variable, which in this case is the velocity. And we extended in order to have the possibility of handling generic and hybrid meshes. So in this context, specifically, we were interested in having hybrid meshes in order to be able to treat complex geometry. And we devised an inexpensive error indicator to drive automatic mesh adaptivity. Automatic mesh adaptivity with tetrahedra. And here I'm representing the 3 levels of mesh refinement near the head of the microswimmer here. In this region, of course, the flow is extremely complicated. There are, specifically due to the complex geometry of the neck of the microswimmer. So we were able to devise a method which is completely insensitive to mesh quality and perform simulation using finite volume in this context. But of course, finite volume methods are still the preferred, are still the go-to choice for the industry and practitioners because of their robustness, but they present some drawbacks in terms of the diffusion and the dispersion error that they introduce. And these are specifically challenging when transient problem and turbulent problem are considered. So the following step was to thinking, can we go high order with this framework? And this is what I want to show you now by means of the hybridizable discontinuous hierarchy method. So I'm focusing now on compressible Navier-Stokes equations. So our equation is this one, and the unknown is this capital U vector, which features density, momentum, and energy. I'm sure many of you are aware of the drawbacks of discontinuous hierarchy methods in this context. Of course, they offer several advantages, like the possibility of devising high-order methods with p-adaptivity in an easy way, also non-conforming meshing. But of course, they introduce a lot of duplicated information with the duplication of all these nodes. This, of course, is critical when we deal with large-scale problems. And for this reason, in 2009, Bernardo Cockburn, Jacob Alakrishna, and Lazarov proposed the framework of hybridizable discontinuous hierarchy. HDG is basically a DG method in which the degrees of freedom within each element are eliminated by means of static condensation. And so we are left only with our unknown on what we call the mesh skeleton, which it's represented by these edges here in 2D and the faces of the elements in 4D. And so our globally coupled degrees of freedom are only the degrees of freedom of what we call U hat. It's our hybrid variable, which lives on this mesh skeleton. And of course, HDG, I don't have time to enter into the details, but I have many more advantages, like it inherits the advantages of BG in terms of going high order, performing p-adaptivity and h-adaptivity. But moreover, it's also robust in the incompressible limit using equal order interpolation for velocity and pressure, which is an extremely powerful tool. So let me show you which is the focus of the research in this context. Again, this is part of Jordi Vilaferret's PhD thesis. Since we are dealing with convection diffusion problems in compressible flows, we're interested in the robust treatment of convection phenomena. So we relied on the framework proposed by Nguyen and Pereire on Riemann solvers in hybrid frameworks. So we are interested in approximating the fluxes F hat, which transport the information from one element UL to its neighbor UR. And specifically, we propose the unified formulation in which these fluxes, these numerical fluxes, are written as a physical flux evaluated using U hat. Remember, U hat is now our variable in the context of HDG. And the Riemann solver is encapsulated in this coefficient tau, which is the HDG stabilization coefficient. So in this way, we are able to devise classical Riemann solver like Lux, Friedrichs, and Roy that were originally proposed by Nguyen and Pereire. But we were also able to introduce a unified formulation for HLL type Riemann solvers, so HLL and HLLEL. And these were specifically interesting because of their positivity preservation and shear preservation properties. Indeed, this is specifically important in the context of supersonic flows. This is a flow, a supersonic implicit flow over Mach 0012. We have Mach number 1.5. And here I'm presenting a zoom near the wind profile, near the airfoil. And what I want to stress is that we are able to use such coarse mesh with these large elements because we are employing polynomial of degree k equal 4, okay? And here we are able to capture the shock that develops in front of the airfoil. Indeed, if we zoom in, we have this representation of the shock using HLL. if instead of HLL we use the Rowe-Riemann solver, we get some weird behavior over here, and this weird behavior is indeed some overshoots of the Mach number, which are extremely localized. Indeed, we can study a little bit more closely the physics, what's happening in the simulation, and here I'm reporting the minimum value of the pressure computed, okay? So the Rowe-Riemann solver, the traditional Rowe-Riemann solver is this line over here. You see that it oscillates a lot. We get negative value of the pressure, and soon enough, the method just diverges. We can make the Rowe-Riemann solver converge by introducing a correction. This is an entropy fix of delta 0.1, and we get the convergence to this blue line over here. But this blue line is indeed physically non-admissible, is the solution associated with these overshoots which are localized. So this solution is indeed not the correct one. And we need to increase the entropy fix to 0.25 in order to retrieve with the Rowe solver the solution of HLL and HLLEM. So, which is indeed the physical one, this one. So the message is that specifically in the context of supersonic flows, there may appear non-physical oscillation in Rowe using the Rowe method. This is well known in the context of Riemann solvers. And these also extend to HDG framework, but this can of course be fixed using entropy fixes, but this is generally speaking complex because it's it needs the parameter needs to be tuned by the user, it's problem dependent, so it may be a little bit complicated, but it can also be fixed using HLL type Riemann solvers, which are robust and they do not require any user-defined parameter. These extend as well to supersonic viscous flows. This is a flow at Mach number 3 and Reynolds number 16,000 over a compression corner. I'm not going through the details. I want to state that this problem is extremely complex because we have a shock wave that develops over here, a shear layer, a compression region, and the interaction of these phenomena. But here I'm reporting the solution computed using polynomial of degree 3 with HDG and HLLEM. And we have an accurate representation of boundary layers. The shocks are represented using a positivity preserving method, and we are able to handle the interaction of these phenomena. So in the context of compressible flows, HLL type Riemann solver offers a lot of advantages with respect to other Riemann solvers in the context of HDG. But all of these, remember that I've talked about incompressible flows early on. So we are interested in seeing whether we are able to perform incompressible simulation also in high order. And this is indeed a collaboration with the group of Van Waal at TU Munich, in which we perform simulation of fluid structure interaction where the fluid was modeled using weakly compressible flows. So Reynolds number here is very small. This was not the goal of going high order, high in the Reynolds number. The goal was about compressibility. And what we are approximating, we are coupling the flow representation through the hybridizable discontinuous Galerkin with a structural approximation, in this case, a neo-Hookean material using high order continuous Galerkin. And here I'm representing the streamlines and the deformation of the wool. If we look a little bit more into detail, the displacement of the tip of the wall, here I'm reporting this displacement as a function of this parameter epsilon, which is responsible for the rate of compressibility of the flow. So as epsilon goes to 0, we are tending towards a perfectly incompressible flow. So we see that the method is robust for different range of compressibility, of weak compressibility actually. And it's also robust in the case of perfectly incompressible flows, which is represented by this blue line over here. So it's robust for weak incompressibility, exactly. It's stable in the compressible limit, and we don't need any pressure stabilization, despite the fact, and this is important, that we're using the same order of the polynomial approximation for both velocity and pressure. Okay, so I've presented you two different class of methodologies. I've started from the construction of surrogate models. I've then switched to solvers. And now I would like to couple the two aspects, specifically by devising surrogate model, which are high fidelity. And by high fidelity, I mean that they are dependent upon a high order solver, which is indeed the hybridizable discontinuous valuing methods that I've just presented. And I will restrict in this case to microfluidics application, because the challenge will come from the parameterization of the geometry of the domain. So specifically, okay. So specifically, we are interested in studying parametric microswimmers. This was part of the PhD thesis of Luca Bertini, in which we parameterize the push-me-pull-you microswimmer. The push-me-pull-you microswimmer is a device composed of two spherical bladders with constant global mass. And we have two parameters acting on this microswimmer. The first parameter controls the mass distribution between these two spheres, and the second parameter controls the distance between the two spheres. The challenge here is represented by the fact that the parameters affect not only the solution, but also the geometry of the domain. So this is very challenging, especially in the context of this microswimmer, because extreme deformations are involved. Extreme deformation, which of course imply also extreme deformation of the underlying computational mesh if we were to deform the mesh. The advantage of the methodology that I'm going to show you is that we rely on a fix. Remember that when we constructed our PGD black box, we rely on simulation performed on a fixed mesh with a fixed geometry, so on a reference configuration. So what I'm showing you here, the video started, yes, perfect, are these two sliders over here, which control the mass distribution and the distance between the two spheres. And here I'm representing online, so this is a real-time evaluation of the solution with the different geometric configuration associated to this parameter and the velocity streamline of the problem. And at the bottom, you see that in real time, there's an evolution of the drag coefficient for the value of the parameter study. So we are able to construct what we call separated response surfaces for the quantity of interest, which in this case is the drag. But we can actually do more, which is perform real-time exploration of parametric solution. So in this case, instead of playing with the sliders over here, we selected trajectories in our parametric space, and we explored in real time how this change of parameter influenced the change of the geometry and the pressure distribution and the change of the drag coefficient associated. So just to wrap up, I've presented you basically three classes of methodologies. The first one is the proper generalized decomposition to construct surrogate models. Then I moved to the face-centered finite volume method and the hybridizable discontinuous valuing method, which provides low and high order frameworks which are robust, meaning they do not rely on user-defined parameters for the solution of flow problems. And eventually, I briefly mentioned mesh adaptivity. Of course, we can also perform degree adaptivity. I didn't have the time to enter into details. But these three topics are basically the three main keywords of this topical collection that I'm editing with Enrique Nadal. So PGD, proper generalized decomposition to construct reduced model and adaptive model. Face-centered finite volume and hybridizable discontinuous valuing are two examples of resolution techniques that may be employed for such problem. And mesh and degree adaptivity, of course, rely on the construction of adapted meshes or adapted polynomial distribution. And all these are presented for application in the context of computational fluid dynamics, but generally speaking, we may be interested in other physics, and so computationally demanding problems for which computational engineering techniques are required. That's it for me. Thank you very much.
Thank you, Matteo, for this very impressive talk. It's indeed nice to see that you are interested in transferring your basic research to industrial applications, and on the other hand, that the industry is interested in your developments. So I currently don't see a question in the chat box. So if you have a question, please unmute yourself and ask your question or type your question into the chat box. I have a question. I think it was on slide 6 when you were talking about the Openform models. So yes. The parameter mu, you mentioned it there. This is not a stochastic.
It's taking forever to go back to the slide. Let me try to be more efficient. Yes, I'm not sharing it anymore. But, so slide 6. Yes, okay, I'm here.
Yeah, but I don't think your
I'm not sharing
is shared.
I will share it. I'm trying to share it in a second. What's happening? I don't see the Zoom toolbar anymore. I don't know. I'm not sure why I cannot share anymore. I don't know what happened.
Let me check here. Oh. Interesting. So maybe I can ask you to share your screen.
Okay, now I see the toolbox again.
Okay, great.
I don't know what happened. Sorry for the inconvenience.
Yeah, no problem. Ah, perfect. Yeah. And we see your screen again.
Yes, I'm not going in full screen in order to be able to switch from slides. The parameter mu, yes.
Yeah, right. Mu. Is this a stochastic model parameter? I don't think so, right?
It does not need to be. In the case that we've been studied, it was not. It was, for example, in this example of the jet flow control was not stochastic, was controlling the peak value of the velocity on the jet patch. But it could also be stochastic a priori. You know, if we were interested in performing some uncertainty quantification analysis, we could consider this parameter mu with some sort of probabilistic distribution as well. Yes.
Great. Okay. So let me check the chat box again. No question in the chat box. Yeah, and here you mentioned that industry is interested, or you have collaboration with Volkswagen in this case. So what about your very nice own flow solver that you presented afterwards? Is industry interested in using this flow solver as well? Your own flow solver?
The Loworder solver, we had some positive reviews in the sense that it's still a finite volume framework, so they are indeed interested in this kind of framework. But of course, they're not so keen to switch from the libraries that they use to another libraries. So there's the possibility. We have some ongoing work with a student trying to see whether it's feasible to implement this field-centered finite volume solver in the context of Openform. In that case, it may be of interest that solver as well, yes. The higher order solver is a bit more green in the sense that there are some additional difficulties because, of course, higher order solver is more precise, but it's less robust. So in that sense, I believe that there's still some work to do before industry may be interested in adopting higher order solvers. For the lower order solver, we have more hopes. Let's put it this way.
Yeah. I can imagine. So industry, it's more expensive, so to say, to use your new full solver instead of using the traditional open form model for industry. I think so. Yeah.
Yes, it's very difficult to convince industrialists to change the platform that they are used to unless they have a clear advantage on the short term, because they have a long time experience on it. So it's understandable.
Yeah, sure.
We are working on it. We are working. We hope to convince them. Yes.
Yeah, that's good to hear. And I see a question in the chat box. Thank you for the very impressive talk. Could the face-centered scheme or approach be implemented in Openform? That's the question.
Yes, indeed. This is this is something that we are exploring with a PhD student, but we only have some very preliminary results on academic toy problems. So there's this possibility, but we don't have a verified implementation yet. But this is exactly what we are working at the moment. Yes.
Oh, that's good to hear. So hopefully the Openform community is interested in the implementation then.
Yes, because I believe that all users of Openform at some point suffer from the difficulty of having a good quality mesh that at the same time was good for Openform, because having good quality meshes, it's doable even for complex geometries. But sure, the good quality meshes that Openform likes, this is a bit of a subset. And so yes, this method could offer a possibility in this case. Yes, this is what we are trying to study at the moment.
Yeah, okay. And then I have another question. I think it was slide 29 when you are talking about tune the entropy parameter, right? 29. About 29. Yeah, here, yeah, that was good. Okay, yeah. Yes, 28. Yes. Yeah, right. Need to tune entropy fix. You said, and I think that is, this is of course right. So, how to tune entropy or the entropy fix? Because it's problem dependent, right?
Yes, exactly. This is a tricky aspect. Indeed, when we started working on this subject, we were not completely aware of the difficulty of this aspect, and this is the main reason for which ROE solvers are generally used in subsonic and transonic flows, but not so much in supersonic flows. Because in supersonic flows, this problem becomes pretty much evident. And what we faced in this context was that we just needed to do trial and error. And if we change the geometry or the Mach number a bit, we needed to retune. Okay, we knew a priori the range of parameter. If this is 0.25 and then we start from a Mach number of 2, we know that we are not going to need an entropy fix of 2. But still it needs to be retuned. And this is what prompted us to positivity preserving methods, because these were the ones that allows us to be robust without the necessity of tuning.
Mm-hmm.
So, yeah. And this is specifically for supersonic, and we've been doing some tests also for hypersonic flows, and in that context, it's even more evident that that having positivity preserving flows is even positivity preserving Riemann solver, sorry, is even more critical.
I see. Okay, great. Okay, so I don't see another question in the chat box. And
in any case, if anybody has a question, can send me an email. That's I'm not sure I put in my email anywhere in the presentation, but I believe you can easily find it from my personal webpage at UPC. It's my name dot my surname at upc.edu. So in case you have any question, any curiosity, feel free to drop me a line.
Yeah, I think it's very easy to find your contact details. Just type in your name and UPC, and then you will be directed to your personal web or business website.
That's it.
Okay, great. Yeah, then we will close the session now. So again, Matteo, thank you very much for this very impressive talk. And thanks for joining us. And to all, have a good morning or good afternoon, wherever you are in the world. And please check our journal's website for upcoming and forthcoming webinars again. Thank you very much and goodbye.
Thank you very much. Again, thank you. Bye-bye.